Okay, geometry, this is 12.6, segment relationships in circles. Please pause the video, come back and check your answers when you're ready. Okay, and easy, easy. We have 4, and x equals 48, and BC is 14. So you set those equal, found y, and substituted. So today, the objectives, you're going to find the lengths of segments formed by lines that intersect circles. Also, you will use the lengths of segments in circles to solve problems. So our vocab today includes secant segment, external secant segment, and tangent segment. So we dive right into a sample here. In 1901, there were divers near a Greek island of Antikythera who discovered several fragments of ancient items. Using the mathematics of circles, scientists were able to calculate the diameters of the complete disks. The following theorem describes the relationship among the 4 segments that are formed when 2 chords intersect in the interior of a circle. So here we have chord AB and chord CD. So remember, the definition of a chord is a segment interior to a circle, endpoints on the circle. So the relationship is that the products of the lengths of the segments of the chords are equal. So what does that mean? So let's look. AE times EB equals CE times ED. So the 2 parts of each chord, when multiplied, equal the 2 parts of any other chord that is intersecting that original chord in the same circle. All right, so we're going to find x and the length of each chord. Okay, so go ahead, pause, see if you can do it, and hopefully you see that segment FE, chord FE, we actually know the values of each piece, right? 7 and 10. And GH, we're missing JH, aren't we? So we don't know both factors here. But what we can do is set it up and substitute the known values. So you should have done 7 times 10 equals 14 times x. So 70 equals 14x, and when we simplify, x equals 5. So don't forget to find the length of each chord, right? So 14 plus 5 is 19, and 10 plus 7 was a given, right? It's 17. Go ahead and pause, come back when you're ready. And you should have set up your 2 chord segments, factors, right? So DE times EC equals AE times EB, and substitute, and solve. And so we have x equals 3.75. Don't forget to find the length of the chords, which are 11 and 11.75. And so here's a little application. The art department is contracted to construct a wooden moon for a play. One of the artists creates a sketch of what it needs to look like by drawing a chord and its perpendicular bisector. Find the diameter of the circle used to draw the outer edge of the moon. Okay, so pause, come back when you're ready. Okay, so it looks like we'll have, if you've already tried it, looks like we'll have 9 times 9, right, equals 8 times the rest of this chord that would be here if we were to create the entire circle. So let's see. We have 9 times 9, and the rest of this chord is the whole diameter, subtract 8. Okay? And so we have 8D minus 64 equals 81, or 8D equals 145 when we add 64 to both sides, and D equals 18 and 1/8 of an inch. Okay, so it started off a little tricky because some of you might have thought that 18 was a diameter, but it really was simply a chord across part of that circle, right? The diameter is a little greater than that. Okay, so we're looking at some definitions here, A segment of a secant with at least one endpoint on the circle. So here's a secant, goes through the circle, but one endpoint is on the circle, right? So PM is called a secant segment. So out here, part of the secant is from N to M. That's outside the circle, right? So we call that an external secant segment. It's a secant segment that lies in the exterior of the circle with one endpoint on the circle. So PM, NM, KM, and JM are secant segments of circle Q. NM and JM are the external secant segments. And so we have a secant-secant product theorem. And let's take a look at this. AE times the external secant segment, BE, equals CE, the entire secant, times DE, the external secant segment. So if two secants intersect, exterior of a circle, then the product of the lengths of the secant segment and its external segment equals the product of the lengths of the other secant segment and its external. So they have a nice way to phrase it here. You take the whole times the outside, which equals the whole secant times the outside. Okay, so let's find the value of x and the length of each secant segment. So we start by setting it up just as we saw. We have whole, they didn't actually put the letters, this is DE times the external secant segment for DE should equal the whole GE, which is 8 plus x, times the external secant segment. And we distribute and solve. And so x equals 6. Since x equals 6, we can say that the entire secant here is 14, right? And the other entire segment had information already given, right? It equaled 16. Go ahead and find z and the length of each secant segment. Come back when you're ready. Remember, whole times the external equals whole times the external secant segment. So we have 39 for LG times 9 equals 13 plus z times 13. And so you should have z equals 14. And your segment's lengths are LG is 39 and JG is 27. So a tangent segment, remember, a tangent line intersects a circle at one point and forms a perpendicular to the radius of the circle, right? So a tangent segment is a segment of a tangent with one endpoint on the circle. So when we add the word segment, we end up with one endpoint on the circle, both in secant and tangent segments. AB and AC are both tangent segments. This is the final theorem of the day, the secant tangent product theorem. And what does this say? It's kind of nice just to start with the conclusion. AC times DC squared, or I'm sorry, AC times BC equals DC squared. So secant AC and tangent DC intersect out here at C. If a secant and a tangent intersect in the exterior of the circle, then the product of the lengths of the secant segment, the lengths which include the interior segment and exterior, or we just call it the secant and the external segment, equals the length of the tangent segment squared, DC squared. So whole times outside equals tangent squared. Let's find the value of x. So we are going to start again with whole times outside equals this tangent squared. So whole is ML, outside external secant segment is JL, times the tangent segment, KL squared. 20 times 5 equals x squared. 20 times 5 is beautiful 100. And the square root of 100 is plus or minus 10. Can a segment be negative 10 units long? Probably not. So we'll say 10, right? That is the value. Find y. Pause the video, come back when you're ready. Okay, you should have again whole times external equals tangent squared, right? And when you substitute those values, we have the whole 7 plus y times 7 equals tangent squared. And subtract your 49, divide by 7, and we have y equals 7 and 2/7. Before we go into the lesson quiz, let's review the 3 big theorems of this chapter. Chord-chord product. If 2 chords intersect in a circle, then the product of the lengths of the segments of the chords are equal. Right? Pretty straightforward. AE times EB equals CE times ED. Chord-chord product. Secant-secant product. If 2 secants intersect in the exterior of a circle, then we have whole times outside equals whole times outside. Secant-secant product theorem. Secant-tangent product theorem. If a secant and a tangent intersect in the exterior, then we have whole times outside equals tangent squared. Whole secant times external segment equals tangent squared. Pause the video, come back when you have your answers. So D is 9, and here are your lengths. Diameter is 8 and an 1/8. Pause and come back with your lengths. X is 10, and the lengths are 8 and 12. And A is 8. Good job. Have a good day.